they will try to keep out your microbes, and they are part of your innate immune system. For instance, so like your skin, it's really impermeable. As long as you don't get like breakthrough of your skin, you cannot get an infection. If you, for instance, cut yourself, okay, that's different. Then you go through your epidermis, and bacteria can invade it, and then you really need to like disinfect it. If you don't disinfect it, those guys come up, phagocytes. They will take up the microbia, and they will expel or secrete cytokines to alert the rest of the immune system. Also, complement is activated. How does this work? Complement binds to your microbes, gets activated, and could ultimately destroy your bacteria, for instance, by making small holes in your bacteria. And then NK cells are very important in fighting viral infections. They recognize viruses or viral infected cells, and they produce a lot of cytokines. One of the major cytokines that is important there is interferon alpha. Does this sound familiar to you guys? Probably, I think, yes. So, and then within those 12 hours, there's also some time for the adaptive immune system to start up, and then you have B cells that can differentiate into plasma cells, and these plasma cells can make antibodies that will neutralize your microbe. And then you have T cells, also those get activated. They need antigen-presenting cells, which could be those phagocytes. So cells of the adaptive immune system can activate your T cells. These T cells get activated, they will differentiate into effector cells, and they will do their effect. So it's not like black and white that you have innate immunity and adaptive immunity, but it really is like it's the overlapping time point. And cells of the innate immunity are involved to activate your cells of your adaptive immune system. Okay. Another way of dividing the immune system is not innate and adaptive, but humoral and cell-mediated immunity. When we're talking about humoral immunity, we're talking about components, effectors that are secreted. And then we think of antibodies, also complement, for instance. Those are effector molecules that are secreted. Most important cell with humoral immunity is B cells. Those antibodies will block infections and eliminate extracellular microbes. While with cell-mediated immunity, you get cellular responses, meaning you get interactions between different cells. So what happens here is a microbe which is phagocytosed by macrophages. Helper T cells are activated, and these activated T cells will instruct your phagocyte to destroy the microbe it has taken up. Same thing for viruses. Virus will infect your cells. These cells will then present viral proteins to cytotoxic T cells, and the cytotoxic T cell will kill your infected cell. Why does the immune system has those two types of immunity? Well, depending on your microbe, you need another response. If you have a viral infection, you don't really have too much use of antibodies. So you need a cellular response. Why? Well, antibodies cannot enter your infected cell, so you need cytotoxic reactivity. So for intracellular microbes, you always need cell-mediated immunity. For humoral immunity, you also need antibodies, or you only need antibodies. You don't really. It's not useful to have activated CD8 cells if you have free living bacteria. So this is actually a way of looking at that. Of course, if you just have like a viral infection in the beginning, you could have, and you have like production of B cells and antibodies, then it could be useful in the first stages, or if your cell breaks open and your viruses will spread. But mainly you need like cellular toxicity. Okay, so what are the effector functions? So for B cells, you have antibodies, and you have, for humoral immunity, you have antibodies production, you have complement activation. if you look at the helper T cells, so the CD4 T cells, they are mainly, like the word says, helper T cells, so they secrete a lot of cytokines, and those cytokines can activate macrophages that can induce inflammation. They can also activate cytotoxic T cells or B cells. Your cytotoxic T cell is mainly instructed to kill infected cells, and then you also have your NK cell, which is kind of similar to your CD8 cell, but it is part of the innate immune system, and it's also able to kill its target when it recognizes it. So NK cells are, for instance, involved in killing viral infected cells in the begin stages of an infection, but also, for instance, can recognize tumor cells. Okay. So how does this all work? I told you, so naive T cells and B cells, they are present in your secondary lymphoid organs, so you have the B cell zones and the T cell zones. Once they get in contact with your microbe, for instance, here you have a microbe that binds the B cell, or you have a microbe that is presented to your T cell, they get activated, and then you have clonal expansion. What's clonal expansion again? Well, if you make T and B cells in your thymus, in your bone marrow, you keep on producing T and B cells with a specificity. They have a receptor very specific for a certain antigen. And actually you make over 10 to the 12 different B and T cells. They are constantly being produced. They will localize to your secondary lymphoid organs. So you have a lot of diversity, but only one or a few of those specific cells will react to the virus. So you need some time for clonal expansion. So your virus or your bacterium induces the activation of one of those 10 to the 12 different lymphocytes. They will start expanding. And then, if you have enough expansion, you really get production of antibodies, production of effector lymphocytes. So the reason that you get sick when you get a viral infection is because you need some time to have enough B and T cells there to combat your infection. Once your infection is actually neutralized, so for instance, antibodies can neutralize them, then of course your stimulus will drop away. So if you have antibodies here, then they will drop away, and you get a reduction of your immune response and elimination of your microbes. So this is like 14 days. At the end, you get your immune system will come to rest, and you get apoptosis, or your cells are suppressed again. Some of them are surviving as memory cells, and those are really important if you will come in contact with the same microorganism again. So maybe let's look what happened here again. So where is this really happening? That's what I just told you. If you have an infection of your airways, for instance, it's those lymph nodes that are really in proximity to your infection. They will get involved, they will get activated. So if you go to a general practitioner, he will feel your lymph nodes at your throat side and not, for instance, in your knee. And that's because that's where the activity is. If they are swollen, this means you're making good immunity. So it's not always a good case. It's not always a bad case. Okay, it means that you have an infection, but it also means that your immune system is working really hard to fight it. So what happens is that the most important cell there are the dendritic cells. Dendritic cells that are underlying your epithelium. They will uptake your microbe, and this dendritic cell gets loose from your tissue, will go through the lymph vessels into your lymph nodes, and at that site they will contact your T cells and activate your T cells. If you have antigens in your blood, they can also be filtered in your spleen. So maybe you should know that blood-borne microorganisms will be leading to activation of T cells in your spleen, while those that are in your tissue will go through your lymphatic vessels and go into your lymph nodes. So this is the first step, antigen uptake and presentation. Actually, if the dendritic cells takes up an antigen, it will change a lot of those communication signals. It will downregulate certain chemokine receptors, and it will upregulate some cytokines, and this will allow it to come loose of the tissue and to migrate to the lymph nodes. For instance, one of the chemokines that's really high here is a chemokine for CCR7, and actually your dendritic cells will upregulate it once you take the antigen. So in this way, your dendritic cell also knows that it has to traffic through your lymph nodes. Okay, so once they're there, they will present antigen to the T cell, and I hope you still know that the T cell needs to get activated by antigens which are presented by MHC molecules. They cannot be activated just by loose antigens. So you can also see during this antigen capture through antigen presentation, your dendritic cells matures. So it will upregulate MHC molecules, co-stimulatory factors, and become a real antigen presenting cell. Okay, so when your T cell is activated by your antigen presenting cell, it will migrate to the B cell zone, and this is the zone where naive B cells are, and also your B cell that it gets activated, it will also migrate to this border. And then you get this very important T cell synapse. I think you heard of that, and this is the way of how a B cell is really presenting antigen to your T cell. Your T cell is giving back signals, and you get formation of plasma cells, and you also get production of antibodies. So for a good B cell response, you need T helper cells, and this is how it goes. So your T cell is activated by antigen presenting cells, will migrate to the border, your B cell get first signals for activation, and you get this very intimate interaction between B and T cells that leads to the activation of B cells and the formation of antibodies. Then you get this formation of germinal centers, and that's actually within these B cell follicles. You get a continuous interaction between T cells and B cells, but also follicular dendritic cells that will also present antigen to your B cell. And during this response, your B cell further matures, class switches, and also forms memory cells. So that's what's happening over there. And then we come into the effector phase stage, and how does this work? Your B lymphocytes are forming plasma cells. They don't have any B cell receptor anymore. They are like producers of antibodies. And these antibodies can have different effects. They can just neutralize your virus, for instance, a virus or a bacterium, which makes them no longer able to infect your cell. They can activate, complement your antibodies. They can also help with phagocytosis. So phagocytes have Fc receptors. If you have antibodies, they can bind to that, and it's a complex of your antigen and your antibody that is then phagocytosed. So probably you know that phagocytes can take up antigens, microbes, and they can do it either by directly binding to this microbe via toll-like receptors, or they can also have Fc receptors that will recognize antibodies that are fixed on your antigen. And that's what this says, Fc receptor mediated phagocytosis. And also they're involved in mast cell activation when the antibody is IgE. And you will hear a lot about this in the lecture on hypersensitivity. Remember that IgE is not only important for allergies, but it's also a very good response to expel parasites and worms. So to get rid of worms, you really need a good IgE response. But if you make a really strong IgE response to allergens, you can get sick. Then you have T lymphocytes, you have your T helper cells. They're mainly involved by producing a lot of cytokines, and your T cell will kill the target. Everything clear so far? Okay. Okay, cytokines. So probably you know what cytokines are, but just like a repetition. So it's a group of soluble proteins. They are the key mediators of immunity and inflammation. A lot of macrophages and NK cells produce a lot of cytokines, and the adaptive responses is mainly the T cells that produce a lot of cytokines. Okay, B cells can also do it, but it's mainly T cells. And these are some of the very important ones. For instance, interleukin-2, you should know actually, is the growth factor of your T cells. The T cell gets activated, will produce IL-2, and will then promote its own growth. IL-4 is important for B cells, IL-5 for eosinophils, interferon gamma for activation of microglia, and TGF-beta as a kind of inhibitory signal for T cells. Important to realize is that some cytokines have different biological effects. That's what we call pleiotropy. So for instance, IL-4, depending on the cell type it will activate, can either induce proliferation or differentiation. You also have redundancy, meaning certain cytokines have the same effect. IL-2, IL-4, and IL-5 can all promote proliferation of B cells. You have synergy, some cytokines work together, but you also have antagonisms. For instance, activated T helper cells that produce interferon gamma will block the effect of IL-4. And this actually also always works in a kind of cascade induction. So activated T cells, for instance, produce interferon gamma. Macrophages are activated by interferon gamma. They will then, in response, produce interleukin-12 and activate T helper cells again. And actually, it's even more complex than it's shown here. Normally, it looks like that. Why is it important? You don't have to know this by heart, of course. Why is it important to realize that a lot of therapies are trying to block one of those cytokines, but you should keep in mind if you block one cytokine, sometimes it doesn't have any effect because you have different cytokines that are redundant, or it could not be enough just to tackle one cytokine because then you have a compensation by other cytokines. It's like you could say one cytokine is a letter, you need different cytokines together to form a word, and the word together with other words will really make your complete sentence, and this is then your immune answer. Okay, so where is it really important and where can you also really use it for therapy is during your stewing of your immune system. So we've talked about humoral immunity and about cellular immunity. What decides if your immune system goes more to the side of the humoral response or to the side of the cellular response? Well, central to that is T helper cells. So T helper cells and the cytokines that are produced when your naive T cells are activated. Actually, you have 3 different types of T helper cells. Like 5 years ago, we only talked about Th1 and Th2 cells. Th1 cells are those cells that will promote cellular immunity, Th2 cells, humoral immunity, and now there's a lot of attention also for Th17 cells. How are these cells identified? Just based on the cytokines they produce. So Th1 cells are those cells that produce interferon gamma, but they don't produce IL-4, IL-5, IL-13. Th2 cells produce IL-4 and IL-5, that's IL-13, but not interferon gamma. And Th17 cells, this is most easy to memorize, they produce IL-17, so it's Th17 and IL-22. And is this just a way of dividing them? Well, yes, that's the way the name got around, but it also means something. So Th1 cells are known to be really important at activating monocytes and macrophages, and they only have a part fixating antibody production. While Th2 cells are really important for humoral immunity, for alternative activation of macrophages and eosinophils. And Th17s, they are quite new, but they're quite involved in neutrophils and monocytes. So when your naive T cells get activated, it depends on what cytokine that's produced, which kind of cell it will really become. And this is what you see here. A naive T cell that is activated, if there's a lot of interferon gamma and IL-12 produced by the innate immune system, they will get upregulation of a factor what's called T-BET, and T-BET activates interferon gamma and other cells, other genes that will ultimately form Th1 cells. If you have a lot of IL-4 when your naive T cells is activated, you get upregulation of added transcription factor, that's gamma-3, and you get the formation of Th2 cells. And then for IL-17 cells, TGF-beta, IL-6, and IL-23 is really important. You get upregulation of ROR gamma-T and the formation of Th17 cells. All these concepts are based on mouse studies. So in mouse it's really clear cut. In humans it's a little bit more difficult. You sometimes also have like mixed phenotypes. You have like a Th1, 2, or Th0 kind of cell. But this basic T cell immunity is mostly based on mouse studies. And it holds true for humans, but it's not like black and white as it is in mice. Of course, mice are held in controlled conditions and they're not exposed to a lot of microorganisms, and this way you can really have a really nice system to study that. Really important is also that a Th1 cell can inhibit the Th2 cell and the other way around. So again, Th1 cells, they make interferon gamma, they activate microglial activation, but this here interferon gamma also suppresses Th2 cells. So you get a kind of balance to either Th1 or Th2. Also the other way around, Th2 cells produce a lot of IL-10 that will then suppress your interferon gamma production and then will suppress your macrophage activation. So in this way you get the balance of Th1 and Th2, and this then decides whether you get a predominant humoral response or a predominant cellular response. You still with me? Yes? No? Okay. So cytokines of Th1 cells do your immune response with cellular response, Th1 cells. They will activate cytotoxic T cells, they will activate neutrophils, macrophages, and they will also promote only those antibody production, those types of antibodies that are opsonizing antibodies, meaning they are again helping to activate your phagocyte. Well, if you look at Th2 cells, okay, so this again Th1 cells. When you look at Th2 cells, they will produce cytokines like IL-5 and IL-4 that will promote the formation of neutralizing antibodies, of IgEs that are important for mast cell activation. IL-5 will promote eosinophil activation and also the formation of IgA, which is important for mucosal immunity. So you see, depending on what cell is mostly produced or activated, you get a shift to humoral or to cellular immunity. Okay, so this is again the same figure showing the same thing. What I already told you. So IgE formation is not always bad. It's also important to eradicate, for instance, worms. So for worms, you don't need cytotoxic cells because cytotoxic cells cannot kill free living elements. So you need IgEs and you need eosinophils, and they then, if they are activated, they also produce a lot of granules and components that will kill this element. Okay. Yeah. So it's a balance, and if it's just normal immunity, fighting infections and so on, at the end your Th1 and Th2 balance will come back in balance again. They actually suppress each other, and this way you get your immune system to rest at the end of your response. In certain instances you get this over overproduction of a certain cell type. If you think about autoimmunity, you get overproduction of Th1 cells. With allergy, you get overproduction of Th2 cells. And there are certain treatments, I already alluded to that. There are certain treatments using cytokines to get this back into line. So anti-IL-4 can be used to suppress your Th2 cell and to enhance your Th1 cell, bring it back to balance, and the other way around for autoimmunity. But you have to be careful, for instance, for autoimmunity. Not all cytokines work in every disease. For instance, anti-TNF works in rheumatoid arthritis because it has been shown that TNF is really important for your cellular responses. But if you treat patients with MS with anti-TNF, they get worse. So it's not always just black and white. Some cytokines have two different receptors, one that is protective and one that is pro-inflammatory, and you really need to be careful with that. Okay. So then you, of course, have your regulation of your immune system, and then you need regulatory T cells. And so the second lecture of today, there will be a lot about regulatory T cells. They're really important at the end of your immune response, when your immune response really stops. They're also partly involved during the activation state. They can suppress activated cells, but they're especially relevant to dampen your immune response at the end. Okay, I think this was my last slide. Any questions here? So again, it's like you need this for the rest of the 2 weeks because it's like basic immunology. Some of the things were maybe new for you, but if you're reading your article, if you're looking at your case, if you're doing your assignment, take this back and see if you could get this to help you with the instructions.